Today on Applied Science, I'm going to show you how I built this EDM drilling machine. No, it's not electronic dance music, but actually electrical discharge machining, and it can do some pretty cool things. One of the key features of the EDM process is that the drill, or the machining electrode, doesn't exert any pressure on the thing that it's machining. So you can drill into the side of a round contour and the bit doesn't stray off like it would with a conventional drill bit. Also, the hardness of the material is not much of a factor, so you can drill through things like hardened steel bearings, no problem, drill bits, even tungsten carbide, which is pretty incredible. This process is also very good for super high aspect ratio holes, and so this is like a 0.7 millimeter hole that's about 30 millimeters deep. Very high aspect ratio. Using a drill bit to do this would be really difficult. In fact, I've been able to drill through every single conductive material that I've found in the shop. So if someone has a suggestion for something else to try that's conductive, just let me know. You've probably done some electrical discharge machining and may not even know it. If you've ever used a benchtop electrical power supply and brushed the leads together and seen some sparks coming out, you've actually been doing a little bit of machining on the leads there. And so if we look at the alligator clip after I've brushed it against the other terminal a few times, you can see that there's actually little craters, little pits in the alligator clip. And that is the result of EDM. So when there's a spark bridging between the electrodes, the spark is very, very hot enough to melt or even vaporize a teeny tiny bit of the metal. And those little craters are now left there because the metal has been either melted or vaporized. The reason that your whole alligator clip doesn't disappear from, striking it on the other terminal like this is that the amount of material removed is very tiny. And once the spark is extinguished, either because the two pieces of metal are in contact now, then there's no more material removal. So the trick to get EDM an efficient process, if we actually want to use this to machine something, is to basically turn the spark on and off very rapidly so that as the bit or the thing that's eroding the material moves in, the spark will form, blow away a little bit of material, but then you want to extinguish the spark right away and then turn the power back on so that a spark forms somewhere else, so that these little craters of material removal happen very smoothly across the whole surface. So the trick is we need a high current power supply at high frequency, like about 30 kilohertz, let's say, that has good current regulation and also the ability to control how long the spark is on and how long the spark is off. And that's what this is. This is the arc generator on loan to me from Bax EDM, and as far as I know, this is the first EDM power supply that is intended for small shops and potentially even hobbyists. So you can build this into whatever kind of EDM machine you want. And today we're going to look at an EDM drill, but another popular one that I'll probably do a future video on is wire EDM. The next part of the system is the motion controller, which is made by a company called Dynamotion. And there's a specific reason that you want to use this particular motion controller, in that it can control the CNC machine in the forwards and reverse feed rate direction. And this becomes really important because in the EDM process, occasionally the electrode will bump into the workpiece and make a short circuit. And you actually have to go backwards to clear the short and start EDM machining again. And there's very, very few motion controllers that allow you to go backwards in your CNC profile. So inside this computer case, I've just bought the Dynamotion boards, and you don't have to put them in a server rack like this. I did this just because it's convenient. For the actual CNC machine itself, I used a kit from Open Builds. This one's called the Sphinx because it has two Y-axis motors, and I can get my tub of water in the middle there without interfering with either axis. And I've been kind of curious about this Open Build stuff. The idea is that the company sends you a kit of parts, including these aluminum extrusions. And the motion feature, the way that they make a slide out of this, is to have plastic sort of skateboard wheels that ride in a track on the extrusion. And I always was kind of skeptical about this, but actually it works much better than I would have guessed. Also, the kit does not have ball screws, but the nut that the drive shaft runs in is like a Delrin nut, and the fit is very tight, so the backlash is very low. I actually measured it myself at about 1/2 thou of an inch in most of the axes here. I used the kit pretty much as designed and just made a few tweaks here and there that I thought improved the performance a little bit. We'll talk about those later. The drill head that I'm using was a bit of a lucky find. Initially, I thought I was going to have to build this whole drill head myself from scratch, and so I was designing it. Also lucky that the open builds thing is in fact open source, and so I actually had the CAD for this. So I sat down and started to do the CAD for a custom drill head, and I realized that I was going to need some custom rubber seals. This is actually what seals the high pressure water into the drill, which is hollow. So I was searching like Alibaba and eBay and all that stuff for these rubber seals. And to my surprise, I actually found an entire complete EDM drill head on AliExpress for like $60. I couldn't believe it. I mean, it was cheaper than the raw materials were going to cost me from McMaster by a lot. So I bought the whole drill head as sort of on spec, and it showed up in a week or two, and what do you know, it's perfect. So you'd be surprised that there's actually not that many EDM drill designs out there in the world. And so basically, if you search for EDM drill rubber seals or whatever, they're pretty much all 9 millimeters in diameter, or a lot of them are, and they all are designed for the same type of spindle and everything. So it's nice that it's rare enough where they kind of, everything is almost the same because no one's really bothered to invent multiple versions of it. The water system works like this. There's one pump here, and this draws water out of the tank and forces it through these two filters that are in series. And these are just standard cheap water filters that I got off of Amazon. Then the clean water comes out here and goes into a T, and one end of the T goes into this airless paint sprayer, which is basically like a high pressure pump that's lower volume than a pressure washer, but is otherwise fairly similar. And the other end of the T comes up here and goes back into the tank. So depending what kind of operation we're doing, we might want relatively low pressure flushing water just to get all of the debris from the EDM process out. Or if we're doing EDM drilling, we actually need a really high pressure source of water, which is why we need that airless paint sprayer. And the reason it needs to be so high pressure is that if the drill rod is, 0.6 of a millimeter in diameter, there's actually a hole going down through the middle of this. And it takes a lot of pressure to get water to flow through this long of a rod with such a tiny internal diameter. So if you're way down at the bottom of a high aspect ratio hole, you still need to have good flow in there to flush out all the chips. And so that's why we need such a crazy high pressure. It ends up being about 1,000 psi, or about 60 or 70 bar, something like that. I should add that in most professional EDM systems, they make a big deal out of the water filtration. If you are running like high volumes through all this, the amount of debris that the EDM process causes will quickly clog up one of these household water filters. And so they make basically EDM water filters that are much larger and just have more surface area to catch the dirt. And then also, you have to control the conductivity of the water if you're really doing this professionally. So you don't want to use absolute pure distilled water because the conductivity is too low, and you can't use tap water because the conductivity is too high. So generally what the pros use is an ion exchange filter, and it measures the conductivity of the water and then sends that through this ion exchange filter to lower the conductivity. Well, I don't have any of that running. Basically what I do is just get a tub of distilled water from the store and use that. And as time goes on, it will get into the right conductivity range. And if you go long enough, it'll probably become too conductive. But it's easier to just throw the water out, water your plants with it, and then dump a new jug of distilled water in. And so far, I've been running this for a couple of weeks and haven't had any problems. So that's been working great. The drill head also rotates just with this low power gear motor. And so you can see it kind of spins the drill rod around. And that's not because there's any sort of cutting tines or anything on there. It doesn't really matter that it's spinning. This just helps keep the system as consistent as possible. So when drilling through, the electrode actually erodes away, not as much as the workpiece, hopefully, but it does erode. And if you're spinning around, that makes the erosion much more even. So the hole will come out more concentric. And having this spin also helps with the flushing process so that there isn't like sort of a channel, like imagine like erosion on a hillside. You don't want the water to keep flowing through the same side over and over. So having this spin around just keeps everything more even. This bracket here is 3D printed. I imported the open builds CAD in and put all this together and then CAD'd it up in Fusion 360 and printed this on the form too. And this is in durable resin, so I could actually clamp down on this and it worked great. I actually printed the threads direct in there. So let's set up for a drill here. Let's cut something. I'm going to unscrew this so you can see how it's built. And there's a Jacob's taper number 0, which is actually holding the chuck to the spindle. So you can see how this is put together. The drill chuck really is clamping down on this so that as it spins, it can positively drive it. But the trick with this whole drill head is that we want to couple, 1,000 psi water into the actual electrode, but we don't want the water, of course, to get onto our chuck or anything else. So what I'm going to do is briefly turn on the water pump, and it's going to force out the rubber seal that's currently jammed in there. Okay, so you saw the seal fall out, and this is what I was talking about earlier. It has these kind of weird looking seals, and the trick is it has to make a good seal with this tiny electrode, or the drill rod basically for EDM. And so it has this channel cut in the top so that the high pressure water actually causes the seal to pinch down tighter onto the rod. So when the thing is assembled, it looks kind of like this, and this is where the water stops. So the water never actually gets down to the chuck. And then in the top side, there's a rotating connection which couples the water from the stationary part to the spindle, which is rotating. So inside here, there's obviously a part that's inside bearings and rotating, and it's hollow and filled with the high pressure water. Okay, so to set this up for a new cut, I'm going to take the old rubber seal off. I'm going to throw that one out, although you can reuse them multiple times. And I'm going to undo the chuck, hopefully. I don't like this chuck much at all. Anyway, it's open, so that's how much electrode is left that we can't really use because of the geometry of the system. So we throw that one away. These are what the electrodes look like, bought new. I got these off of eBay, and they are purpose-built for EDM drills. Very common is using brass electrodes, and the reason for that is that the blend is copper and zinc. That's what brass is. And the copper is good because it has good electrical conductivity, and the zinc is good because it vaporizes very easily. So as this thing is drilling down into the material, the electrode is being eroded as well as the workpiece. And we don't want sort of gobs of molten metal sticking in there. It would be much better if it vaporized and then sort of made like a smoke almost that the water carries away. So the zinc is better at being turned into smoke. So we'll put the electrode into the drill chuck. I actually cut these electrodes in half just because this machine is not quite tall enough. And I'm going to use a new rubber seal, and it's actually completely sealed at the top, so it actually pierced through there. I'm going to stick this out just a little bit more so that the seal can basically go down to really small diameter drill rods. In fact, it's not uncommon to get down to like 300 micron that still have a hole down the middle. It's really quite something. So that's in there. And then on the bottom side here, this is the Electrode Interface Er that I came up with myself, which I don't know if this is really pro or not, but it's basically just a piece of brass with a hole that's very, very closely matched to the electrode diameter, and it's sitting in a 3D printed piece of plastic. And then the thing that is mounted in the plastic is actually a ceramic bushing, which is purpose-built, again, for EDM drills. And you'd think all this is like really specialized, hard-to-get stuff, but actually this also came from eBay in the same lot where I got these electrodes. So it's easier to find some of this stuff than you might guess. Initially, I tried different things to interface the electrical connection from the arc generator to this electrode, and I had like spring fingers and stuff that were pinching it. But the problem is that if you apply any force, any side force to this drill rod, it causes the thing to be wonky, right? Like if you're going through here like this and you're applying force to it, you will have concentricity problems. So I eventually settled on a bushing, which is perfectly concentric with the axis of this whole thing, and it's conductive. So, even though there isn't like spring tension holding it on there, I haven't had a problem with a loss of conductivity. So what we'll do is thread this through, and the fit is tight enough where if there's even like a tiny burr on the end of this drill rod, which there is, I can feel it won't go through. So let me clip the end of this. I'm basically just going to cut a very slight taper on there. And hopefully that'll help us thread through. Okay, let's see if we can thread this through. There we go. So now it's threaded through the brass, through the ceramic bushing, and then I'm going to head back up into the spindle here and tighten this down. And this is not a, it's not like it's tightening down to whatever I feel is tight. It actually goes into a hard stop. So once I've tightened that down, it's basically bottomed out, and that's it. And now the machine is pretty much set up, so let's drill something. The cutting force is very close to zero because the electrode actually never touches the workpiece. It's only the electrical arcs that jump between them, ideally. But remember, since we are blowing water through here at such high pressure, there will be a little bit of force. However, the clamping requirements are basically nothing because there is so little force here. And I have one lead connecting through the water, just alligator clipped on. And for small holes and stuff like this, the electrical connection is really not that critical. Okay, so what I'm going to do is jog down so that the electrode is just about to punch through, and then we'll turn the water on and drill a hole. The software that comes with the Dynamotion controller is really deep and full featured. You can program it to do almost anything you want, and you can also program C programs and FPGA code that gets downloaded into the controller. So you can literally create anything you want. The downside of this is that the learning curve is really brutal. Luckily, Mike Bax, the creator of this arc generator, has written his own C program that will control this controller as if it were a purpose-built EDM machine. And sort of the main thing here is that when there's a short circuit, or when the arc length is getting very short, like there's about to be a short circuit, it tells the controller to back off the feed rate. And I mentioned that most controllers can do this, right? Like imagine you're running a milling machine. You have a knob where you can turn the feed rate from 100% down to 0% or 200% or whatever you want. But the trick is almost no controllers have negative % feed rate. It's almost unheard of. It wouldn't make any sense for a milling machine. But for EDM, like I mentioned, if there's a short circuit, you actually have to back up to clear that short. And this happens, occasionally, like once every minute or once every 10 seconds, depending what you're doing. And the K-Motion controller does this by an analog link that goes from the arc generator back to the motion controller. So there's basically just a voltage that tells it how long the arc length is. And when it gets too short, or even if it's 0, then it tells the machine to back up. And so all that's been programmed in, and you can just download it and get it going, although there's still quite a bit of setup. So we have controls over this, and we can turn the arc on and off and run G code just like normal. And in this case, I'm just going to type the G commands in. We can jog the machine like this. Okay, so I'm going to turn the water pumps on. The main pump, turn on the rotating spindle, and I'm going to turn the high pressure pump on. So now we've got about 1,000 psi, and there's water flowing through the electrode. And you'll notice that the spindle actually goes a little bit slower when the pressure is on it, of course, because that rotating seal has all the force on it now. And you'll hear the pump turn on and off. This is how airless paint sprayers work. It actually has a pressure switch inside there, and when it senses the pressure is too low, it just runs long enough to get the pressure back up. So that's totally normal. Okay, so I'm going to run the code that initializes the machine and then sets the feed rate based on the arc length. And I'm going to drill straight down. I forgot to add that the arc generator can be programmed with different currents and on times and off times. Like I mentioned, that this is an important part of getting a good cut going. So when I started that cut, the power was way too low. So I'm going to turn this up to about 15 amps, which is kind of mid-scale, and put both of these at about mid-scale. So arc on time is like 15 microseconds, off time 36 microseconds, and that gives us a frequency of close to 20 kilohertz. So when I say send config, all of this is downloaded to the arc generator. And now when we go back to the screen here, I'm going to run that G command, the G code, and it's going to use the new settings basically. I mentioned that the arc length is reported from the arc generator to the motion controller via this analog voltage. And so the voltage corresponds to the arc length, and when it gets too low, that's when we go into this reverse feed rate control. And so you can see in some of the other cuts that I've made, the machine doesn't just plow forward, it actually can sense what's happening, which is a critical part of this whole EDM. So let's go back to the workpiece and I'll hit start. You can see it in action. And it will pick up speed as it notices that the arc is stable. You can see some gas bubbles coming out there. Here's a shot from an earlier setup, just so you can kind of see what it looks like in profile. Cutting speed can be pretty high, especially in aluminum like this. I haven't tried to find the limits, but it can easily cut at maybe, oh, I don't know. I've seen it go as fast as maybe about 1 millimeter per second at this sort of setup. So the electrode is all the way through, and as it goes through, it's making the hole slightly bigger because of lack of concentricity there. So as you can see, I wasn't really paying attention there, and the electrode, it must have been bent or something, because the hole that it created is much larger than the electrode itself. And that will happen if there's a bend in it. Because we're spinning around nice and consistently, the hole will always be round, but it might be a slightly larger diameter than the electrode. In this case, since the thing was bent or there was something out of alignment, the hole is quite a bit larger. However, you might be thinking, hey, wait a minute, this is useful. If you chuck up a big solid piece of brass, like a 1/4 inch, you could actually pretend like it's an end mill. And that is in fact a thing that we'll look at in a future video, EDM milling, which can be really useful because your mill can be square. If you aren't rotating it, you can have a sharp edge thing and drive it into the corner of a box to get like a sharp internal edge. And this is pretty common in sinker EDM, which is yet another kind of EDM process. One thing that you have to watch out for is electromagnetic interference. The EDM process is inherently very electrically noisy. Like you've probably heard of spark gap transmitters. Well, this is one heck of a spark gap transmitter. It's got, 15 amps going and 30 kilohertz might be the switch frequency, but the actual frequency content of the waveform is probably much higher than that. And that will in fact cause interference with electronics. And the Dynamotion motion controller boards appear to me to be slightly more susceptible to EMI than sort of standard electronics. I mean, these are sort of custom-built boards. And so you have to be really careful and put ferrite beads on everything and ferrite toroids and make sure it's grounded and shielded and everything. But what you see here is, I would say, medium effort. I haven't gone completely nuts and ended up not having any problems. So let's open up that let's open up the computer case there and I'll show you the Dynamotion boards. Okay, so here we've got a 24-volt power supply that runs the stepper motors, and the power supply goes into the stepper motor driver board, and the stepper motors are connected through a DB25 connector that comes off of here. So this is actually the stepper motor controller that's also produced by Dynamotion. And the stepper motor is driven through this Cat5 cable. This is like step and direction signals that come out of here, and this converts it into the stepper motor actual drive current. The actual Dynamotion controller is this board here, and it's piggybacked onto an analog input board, which is used for a few things, but mainly it's that feed rate override control that I was mentioning. So this is the actual 10-volt signal that describes how fast the machine should be going. And if that signal is too low, let's say 2 volts or whatever, it actually goes into reverse feed rate. So pretty standard stuff. I just got a 5-volt supply over here just to run the logic. And there's a couple of auxiliary ins and outs to control things like water pumps and that sort of stuff, but I haven't really hooked any of that up just yet. Okay, like I say, I'm probably going to do another video on wire EDM, which is kind of like the complement to this. If you use hole drilling EDM to make a hole in something, you can then feed a wire through and then move the wire around to cut like a complex 2D shape out, or even 3D. Okay, hope you found that interesting. See you next time. Bye.